Hello students, welcome back. Previously, we went through some elementary substitution type problems. There's some more, and these problems are going to be a little bit harder, but still they're elementary. So let's go ahead and do this. So let's take a substitution, say u as, okay, good question. What's your substitution? There's no question, you have to substitute this one. As for the inside of the composite function, do you see this denominator? You cannot separate the denominator, you're stuck with that, so that's a good candidate. So there is a substitution number one, and then let's take the derivatives. So we got that, and then you can solve for dy. And finally, so okay, we got this blue as well. So in this original integral, we have fractions, so let's take a little bit larger fonts to see it better. And this can be rewritten as u here, no question there. And then this one here, you can replace like this. Let's bring back the color. Okay, so far so good. Now, do we have simple integral? Well, yes you do. You do have a simplification. How? We get y plus 1 over u, and times we have 1 over 2 times y plus 1 du. You see, 2y plus 2 is twice of y plus 1, so we do have simplification. In the end, what do you get? We have integral of 1 over 2u. Okay, so what's the antiderivative? Log of 2u plus c. Is that right? Wrong. No, that's not right. That's not how you handle the antiderivative computation of the reciprocal function. This is wrong. You can rewrite like this. 1/2 times 1 over u like that. Or even better, u to the negative first power like that. So we have log of u. 1/2 log of u. Therefore, 1/2 log of, what's the original? Y squared plus 2y. Here, the third substitution went through. U equals to y squared plus 2y. Okay, a little bit harder, but still elementary. Yeah, same as the solution here. How about this problem? Let's take, say, let's say u again. And what's the inside function? Just like the previous problem, if you take the denominator, you're going to get something like this, and then the derivative will be what's the derivative computation? By chain rule, 1/2, and the 2 plus cosine of x to the negative 1/2 power, so 1/2 square root of 2 plus cosine of x, and then negative sine of x dx, and then how are you gonna solve for dx and so on and so forth? Well, it may work, but it's not promising. Yeah, we do have sine of x popping out right over here, so it may work. Maybe not, but maybe you do it. In any case, it's not the best. My suggestion is to take the inside of the composite function, that is inside of this entire radical. Not just a denominator, because this is just inside of negative 1/2 power function, basically. And then we can take the derivative. And so for dx, 1 over negative sine of x du. So we both have these. Let's increase the font so that I can see things better. That's nicer when you have this fraction integral here. And this entire thing became u, and this dx is replaced by this quantity here. Let's highlight this one back in blue. And did you get a simple integral? Sine of x, the sine of x cancel out. We get a negative 1 over square root of u du. So this is much more manageable integral. Okay, what's the antiderivative? Log of square root of u. Wrong. Wrong, wrong, wrong. Correct it. How do you make it right? Don't pay too much attention to this reciprocal expression, 1 over something. This, as a matter of fact, is a power function. Not the reciprocal function, a power function. U to the negative 1/2 power function. Why negative? Because u is coming from the denominator. Why 1/2? Because it's square root. And this negative, of course, coming from this negative, which was there before. So this antiderivative computation will become negative of u to the, well, add 1 to the power, and then you have to divide. So 2 over 1 plus e. So this is negative 2, and what is u? 2 plus cosine of x to the 1/2 power. So this u is 2 plus cosine of x. That's the final substitution. Remember here, do not just go ahead with log function. I see that mistake really a lot. Change it into a power function. Unless the power is -1, it's not going to be a log function. Okay, all right, we got that. How about the last problem? We have integration by substitution problem, but this does not look like substitution at all. It doesn't look like it's a composite function. How do you work it out? Well, one way to do that is to look up the integral table and find out the antiderivative formula for tangent function, because it's such a simple function that you can readily find out. But if you want to deduce that, you can do it this way. Rewrite this tangent as sine over cosine. And then if you do that, you'll see that the denominator is cosine, and that's a substitution that you have to work out. And then also, the derivative of cosine is sine. So, how will you do this? Let's take which character you choose. Okay, alright, I'll choose u, cosine of t. The derivative is negative sine of t, dt. So dt is negative 1 over negative sine of t du. Okay, all right. Put everything into this integral. And then this thing becomes what? The denominator, cosine of t, is just u, and dt is this quantity here. So if you do the simplification, oh boy, it's going to be better with a little bit bigger font. Sine of t, cancelling out. You have integral of negative 1 over u. Does it look good? So this entire thing is going to be negative log of u plus c. And consequently, you can rewrite it as negative log of cosine of t plus c. Final substitution, u is cosine of t. And that completes the problem. You can simplify this a little bit further, and if you do that, and then this becomes log of 1 over cosine of t using the log rule, and then this is log of secant of t plus c, and this final form appears in the integral table if you look up in the textbook or internet anywhere. Integral formula for tangent function. But as far as this problem is concerned, you can stop here. Okay, so much for elementary problems. Let's meet again with a little bit more advanced problem in a separate video.